When installing a step-up transformer, understanding the grounding requirements is crucial for safety and code compliance. Firstly, let's consider the equipment grounding conductor, often abbreviated as EGC. In this specific scenario, an equipment grounding conductor from the main disconnect to the transformer is not required. This is because the neutral is already bonded at the main disconnect. Typically, an equipment grounding conductor is necessary for delta-connected systems. However, in this situation, the transformer is supplying a 480 volts delta system from a 208 volts Y system. This configuration does not create a neutral on the secondary high voltage side, negating the need for an equipment grounding conductor between the main disconnect and the transformer. Secondly, let's address the grounding electrode conductor, often abbreviated as GC. Unlike the equipment grounding conductor, a grounding electrode conductor is indeed required. It must be run from the transformer to the grounding electrode system, often abbreviated as GES. The grounding electrode system is the network of grounding electrodes present at the building. This connection is essential to establish a reliable, low-impedance grounding path for the transformer, providing a path for fault current back to the source. Now let's look into grounding electrode conductor sizing. The size of the grounding electrode conductor is directly related to the size of the ungrounded conductors or overcurrent protection device, such as a fuse or circuit breaker protecting the feeder supplying the transformer, and is selected from the appropriate table in the National Electrical Code, often abbreviated as NEC. In this case, the feeder is protected by 450 amps fuses. Based on this, the minimum grounding electrode conductor size should be 250 kcmil copper or 350 kcmil aluminum. These sizes are based on standard NEC tables and assume that the grounding electrode conductor is connected to a suitable grounding electrode system. Always refer to the latest edition of the NEC and local codes for the most up-to-date requirements and specific table references. For example, refer to NEC Table 250.66 to determine the size of the grounding electrode conductor. Also, the flex used for the final connection to the transformer must be appropriately rated. The flex must be rated for at least the maximum current that can be drawn from the transformer. In this case, the transformer is 75 kVA and steps up from 208 volts to 480 volts. To calculate the maximum current in the 480 volts side, use the formula kVA times 1000 divided by volts times the square root of 3. Therefore, 75 kVA times 1000 is 75,000 volt amps. Divide this by 480 volts times the square root of 3, which is approximately 831. Then 75,000 divided by 831 is approximately 90 amps. It is essential to select flex that can handle this calculated current of 90 amps. Keep in mind that this is the calculated full load current. You must also consider any applicable derating factors and overcurrent protection requirement. It is good practice to choose a flex with an ampacity higher than the calculated current to provide a safety margin and ensure reliable operation. Finally, always install the transformer according to the manufacturer's instructions, relevant national codes such as the NEC, and any local codes and requirements imposed by the authority having jurisdiction, often abbreviated as AHJ. Adhering to these instructions and codes will ensure a safe and compliant installation. In summary, for this specific setup, you do not need an equipment grounding conductor from the main disconnect to the transformer due to the neutral bonding at the main disconnect and the delta configuration of the high voltage side. However, a grounding electrode conductor is required from the transformer to the grounding electrode system. Size the grounding electrode conductor based on the size of the feeder conductors or overcurrent protection device protecting the transformer, in this case 450 amps fuses, and select the appropriate size from NEC Table 250.66. Furthermore, ensure that the flex used for the final connection to the transformer is rated for at least the maximum current that can be drawn from the transformer, which is approximately 90 amps in this case. Follow the manufacturer's instructions and adhere to all relevant codes and regulations. By following these guidelines, you can ensure a safe and code-compliant transformer installation. Remember that electrical work can be dangerous. Always take appropriate safety precautions and consult with a qualified electrician if you are unsure about any aspect of the installation.